Good morning, everybody. The title of my talk is, thanks, Alan. The title of my talk is Private Signaling, and this is with my amazing collaborators, Alessandra, Scafuro, my advisor, István, Omer, and Denis. All right. Sorry. OK, so I'm going to first introduce the setting, and the setting is that of anonymous messaging, where you have many senders and receivers, and we assume that there is no pre-shared secrets between these senders and receivers. Okay, and the only way to communicate is through this public bulletin board. You can think of it as a blockchain. And if Alice wants to speak to, say, Bob here, Alice would broadcast this message to the network to say, hey, I'm going to encrypt this message under Bob's public key, and just post it to the bulletin board. At a later point of time, when Bob wants to decrypt this message, he's going to look through the blockchain, find the corresponding ciphertext, decrypt it, and read, hi, Bob. All right. And this is sort of like a sender-receiver communication. And like I said, it's happening over this public bulletin board. All right, so now how would Bob potentially try and retrieve this message? I'm just going to go over two naive solutions. The first one could be, Bob just tells the server who's holding this blockchain to send over the entire state of the blockchain. And the server sends over the blockchain. Bob tries to decrypt one by one until he receives, he retrieves the message that says, OK, this is the one that decrypts correctly, and this is my message. Or the other alternative would be that Bob says, hey, man, this is my secret key. Can you try and decrypt all the messages that you have and find the one that is for me? The server could do this, but then now the server knows exactly what the message is, right? And Bob can decrypt it, but there is some, I guess there is efficiency here, but there's no privacy here. So what I'm trying to get at is that there is this inherent tension between anonymity and efficiency in this setting. And the idea is that if you want great anonymity but very bad efficiency, you just download the entire blockchain, right? And then you have to do sort of ON work, where N is the total number of messages that are on this bulletin board. And if you want great efficiency but no anonymity, you just give your secret key to this server who is holding the entire list of ciphertext, and you ask him to decrypt your message. And such a situation or this setting is not new. It does. Oh, I'm sorry. Before that, what I would like to say is that in this work, what you're trying to do is trying to sort of look at this particular situation where can we get great efficiency and anonymity for the receivers. That is, we want the receivers not to do too much work, but also at the same time maintain their anonymity. All right. And such a situation does already arise in cryptocurrencies, for example. Especially with that of Zcash, where there are private transactions, and private transactions are posted to the Zcash blockchain, and at some later point of time, say a party wants to come and try and find its transactions of the blockchain, but they're all private, and it's going to be hard for the receiver to find it. And this also comes up in Ethereum, for example, when they were trying to come up with stealth addresses, and in fact, this was the starting motivation for our this paper as well. All right, so now maybe I'll just go into some more detail on what do we want, what are we trying to do. I'm just going to try and formalize it. Before that, I'm just going to mention the actors in our setting. So we have a sender, Alice, we have Bob, and we're going to call this new service called a signaling service. And this signaling service basically is going to do some work such that the receiver does not have to do the whole work of going through the entire blockchain and trying to decrypt everything. So in some more detail, how this is going to work is that the sender originally would have posted some ciphertext onto the public bulletin board, as I described earlier. And the sender then says, hey, so my message is in position 10 of this public bulletin board. Let me send a signal to Bob about this location. So the sender then writes this signal also to the bulletin board. The signaling service is going to read these signals, do some processing of these signals, and then at a later point of time, when the receiver wants to get the message, he's just going to ask the signaling service and retrieve the locations of his messages on the public bulletin board. And then he knows, OK, my message is on the 10th position, and he's able to decrypt that ciphertext, say, efficiently. We don't talk about that in this work. The only thing that I want to look at is how the receiver can just get his message from the bulletin board. All right, what do we want concretely in terms of efficiency and privacy? we want that the sender is just, nothing changes for the sender. That is, he should not be, the sender also should not be doing extra work. The sender should be doing exactly constant work per message she wants to send to, say, Bob. And there are no privacy implications for the sender. For the receiver, what I want is that the receiver should only be talking to this server and also should do constant work per message received. So originally, if this receiver had to decrypt all the messages, he would have had to do O(n) work. But I want only O of 1, that is just constant work. And that the privacy goal that we're trying to achieve here is that nobody else other than the receiver learns information on these signals. And lastly, for the signaling service also should just read the blockchain and do some processing of these signals and should be able to return these signals to the receiver. And the privacy guarantee is that the server will, of course, know when a receiver is going to retrieve, say, his signals, but does not know the location of the messages that are on the board, does not know what these signals actually contain. And we assume some rational behavior for the signaling service, that the signaling service will, of course, do what he is supposed to do. But otherwise, the signaling service is trustless, as I will show how I'm going to instantiate the signaling service. And in our work, we modeled this in the UC framework. So all the proofs and security theorems are in the UC framework. All right. So now I'm going to proceed to explain how we actually instantiate this. First, I just want to explain a general approach where there's no privacy, and then I'm going to add privacy on top of this. All right, so with the general approach would be, Alice wants to say, send to Bob that, hey, on the 13th position on the board exists my message. So what would Alice do? Alice would, just send this message, say, publicly on this bulletin board, Bob 13. The signaling server reads this from the board and just writes 13 to this table of signals that the server maintains, where, for each row corresponds to, say, the receiver's identity or something. At a later point of time, when the receiver comes and says, hey, I want to retrieve my set of signals, the receiver is just going to, say, somehow authenticate himself, and the signaling service returns the entire row back to, that row of signals to Bob. And ideally here, what we would also do is that we would just flush out this entire row. The signaling service would make this all zeros so that you can process more signals in the future. All right. So now, if I want to add privacy, ideally what would I need is this table should be encrypted, and I should find a way to obliviously update it. So now I'm going to replace that table of signals or the positions with encryptions of these positions of messages, and this is what I call a signal. And there are a couple of observations that we should make here. The first one is that the signaling service, after it does an update of any signal, should ideally update all the ciphertext. Otherwise, some information is going to be leaked to the server trivially, right? So for example, if only one row, for example, Bob's row was, say, updated, then this server at the end of the operation knows that, okay, Bob was the one who received this message. And the second observation is that we have a fixed number of messages that a particular receiver can receive, and we denote this as L. And like I said earlier, after every retrieve operation, the signaling service is just going to flush out these messages so that they're like encryptions of 0 instead of encryption of the actual locations of the messages. Okay, so now maybe to the more interesting aspect, like how do we accomplish these oblivious updates? So in our paper, we present two solutions. The first one is with a two-party computation. And here we assume that we have two non-colluding servers, and two semi-honest servers, and they together are going to maintain the table that I described earlier. And the second solution is with a trusted execution environment, where whatever table updates are going to happen, that's happening inside of the TE. And for the interest of time, I'm only going to explain the solution based on the two-party computation as opposed to the TE. So the idea is that, like I said earlier, the two servers together are going to maintain this table. So it's just basically that if you XOR these two tables, you should get the original table again. Like in each position you XOR, you get the original table. And what is the original table? Basically each position contains a signal, which is basically the position of the message on the board. All right, and just to go over the protocol, what would Alice do here? Alice would, so say we start again with the identity Bob, and the position is 13. Alice creates XOR shares of the identity as well as the location, and encrypts under each of the public keys of the server the location as well as the location share and the identity share, and just post this to the blockchain. Now, to process, the two servers are going to run a two-party computation. That is, they're going to send garbled circuits to each other for some function f, which updates the table of the other party. As you can see, the input of the table, input of the garbled circuits is like his own table. The share that he receives from the shares of the location and the identity that he receives from the sender. And what does this function f do? So the function f does two things. The first thing is that it tries to find the identity of the receiver, like just by doing an XOR of the identity that it receives, and inserts the share of the position that he received from the sender. And the second thing this function would do is just re-randomize the entire table. And we need this, like I said earlier, so that no information is leaked to the servers on the location of the message that is on the board. So far now, the two tables are then updated with just the shares, right? And how would Bob, say, retrieve? Bob, this is fairly straightforward. Bob would just somehow authenticate himself, say, hey, this is my signature, I'm Bob, and I want to retrieve my rows. The two servers just respond with the corresponding rows. Bob just needs to then just XOR these two rows, and he will get the locations of the messages that are on the board. All right. So far, so good. So this is, this ends the protocol that I wanted to explain. Now I'll just go over some cool related work that is very similar to, what we do, or it's similar to the same problem that they're trying to solve. And the most related work is that of Oblivious message retrieval by Liu and Rantromo. And this is going to be presented at Crypto 22. And this is cool in the sense that they make use of only one server, and do not require any, say, TEs or anything, but they rely on fully homomorphic encryption. And they sort of have the receiver still do O of log n work, where n is the total number of messages on the board. So their result is slightly less efficient than us, but though they don't need to, even with their one server model, they don't need to rely on any trust assumptions like TE, for example. And the next work is that of fuzzy message detection by Beck et al., which is presented at CCS last year. And here the idea is that, again, there's a single server who has a fuzzy key. And this key basically identifies ciphertexts that are pertinent to a receiver, as well as some false positives. So here in this setting, so you have sort of like a trade-off between efficiency and privacy. So if you want less false positives, then you're revealing more about your identity to that server. And on the other hand, if you want great anonymity, the receiver basically receives all the ciphertext as false positives. So in conclusion, I'd like to say that what we did was we presented a UC definition for this problem of private signaling. We presented two protocols, one based on two-party computation and another one on TEs. So our protocol, as of now, gives the best efficiency guarantees to the sender and the receiver. That is, they need to do just constant amount of work per message sent or received. And for future work, what we would like to do is sort of come up with constructions to reduce the computation of the server. As of now, the server needs to do order of the number of receivers computation per signal. And we would also like to remove the assumptions of either maybe non-colluding servers or that of TEs for a single server construction. And with that, I'd like to thank you. You can reach out to me at this email address, and you can also see the full version of the paper at Solink. Yep. Thank you.